Okay, thanks, Roger. Let me just hopefully it's almost 10 o'clock in the morning here, and after 3 or 4 days of rain, I'm looking forward to getting out and doing some stuff in the garden, even though it's midwinter. Is my screen visible?
It's off center, but it's there.
You can only see part of your presentation screen.
Oh,
Nice desktop with a comment.
Maybe share an application instead of your entire screen.
There, now it's in the center.
can you see the full title?
Yes.
Yes.
Okay. This first presentation, I'm focusing, it's very much a global picture and try to give you an idea of what's happening around the world as distinct from any one particular region. The growth of observations, as you can see from this plot, it's going up exponentially now. I've shown this plot before. We increase it as years go on. The last column is
David, we're still seeing your first introductory slide, not the image.
I think you're sharing the wrong screen. You should share the presentation and not the full screen.
Okay, I will.
Is your presentation maximized?
Well, it was. Hang on. No, I won't. Oh, now I've lost the. Why won't that? I've lost the controls on the bottom of the Zoom screen.
I'll stop your sharing, Dave, so that should come back here. There we go.
Yeah.
Okay, that should be
okay. Share screen. Oh. Is that showing properly?
That's better.
Yes, that's
perfect.
good.
Okay.
Yes.
Okay, there's the, is that graph show or plot showing?
That's the one.
It does,
Right.
and I'll point out that we can see your cursor move too, in case you want to use it to highlight anything.
Yeah, that's good. Yes, you can see the growth at the recent years. The Gaia DR3 is had an impact, but also in recent times, I think it was April this year, Horizons, they ingested the Gaia DR2 asteroid observations into their database and orbit solutions, and that has had a significant improvement on their orbit solutions. So I expect our numbers will increase. The numbers for 2021 are up to around about the end of May. I'm expecting we'll go over 1,000 observations, successful observations this year, which is putting a heap of strain on our global resources. This is an interesting plot of our successful observations, how many are usable as distinct from those where when you look at the data, you say, can't rely upon this observation. Early years, well, 1994 was the worst, with almost all of them being useless. Whereas back in current years, it's only about 3% of our successful observations are being totally rejected. Now, when I say rejected, they're still in the in our database, but we flag them as being unreliable. This is just a quick show of listing of our worldwide observer group. So this is around the world. Of our successful observations, we had 405 observers. And you can see there the number of observations per year in the regions. Europe and North America run neck and neck. They've done that for years. Australasia, we've got a huge number given the sparsity of our population where they're located. Japan got a small number because Japan covers a small area. A thing to particularly note is the distribution of observations by asteroid diameters. Ignoring Europe, most observations are in the range of the 20 to 50 kilometres and 50 to 100 kilometre, or 20 kilometres and larger. You can see the type of pattern there. Europe is different. They've been very successful at recording occultations of small asteroids, as you can see from those figures, which is something to note. The astrometry from small diameter asteroids is very good. The smaller the asteroid, the higher the accuracy, which is an interesting thing. This is the first time I've generated a plot like this. Ignore the star on the right, I forget why that's there. What this shows is the number of occultations per year divided up by the number of chords observed in that reported occultation. The top line, the brown line, you can see how it has grown rapidly over the years. Now they're single chord observations, and currently single chord observations are by far the most common observation. The green line, 2 to 3 chords, that's also been growing at a reasonable rate. 4 to 9 chords, a bit of growth, and 10 or more chords. Over the last 15 years, basically no growth whatsoever. So our ability to get detailed shape, orientation, measurements of asteroids by the occultation technique has not really changed over the last 15 years. The purple and green lines are observations where we can measure the size. Green, you can get broad shape, and you can get astrometry from all. But it's an important thing to understand where the growth of our observational results is going, which is very much single chords, which is astrometry. This is another interesting plot. It just shows the number of chords by region. The 10 or more chords, Australia's got none because of our population distribution. Japan's got proportionally a very large number because high density of observers in a small country. Europe, interestingly, has more than the US, but that's because of their high density of observers through Europe. Anyway, enough on that because time is short. This just shows the number of observations versus the number of events. Back in 2000, on average, we had almost 7 observers per successful event. For the last 5 years, 10 years even, we're averaging out at about close to 3 observers per successful event. And that seems to be a long-term trend, for whatever that means. Here's a number of successful events by region. Again, you can, if you look at the 220 column, you can see the numbers there. Similar to the previous one there. What's surprising me is when you look at this current year to date, in Australasia, I'm not quite sure why, but to June, we've had as many observations as we had in all of last year. Whereas North America, you're on track to have about the same number as last year. Don't know what the explanation is for the trends. Europe, there's some reporting delay issues associated with Europe. Most other regions, the reports come in, well, I get them within 2 months of when they've been made. Double stars, we regularly discover new double stars. Diameter, separation usually 1 to 100 milliarc seconds, and resolution of Gaia is about 100 milliarc seconds. Solution is not always unique, but if you have several observers, the uncertainty in separation can be less than a milliarc second. This is just a list of the double stars which were discovered last year. There's 9 of them. Some of them, you've got a single solution, so it's a well-defined solution. Others, usually single chords, and the solution is not well-defined. These all get reported in the Journal of Double Star Observations. Martin Unwin in New Zealand is handling all of that. And anyone that observes a double star type event, make sure you send a report to Martin in New Zealand. Binary asteroids, an issue of it's quite topical at the moment. So what have we observed this year? We've had 1 suspected satellite. We've had 1 known satellite, 90 Antiope, or however you pronounce these things, plus 1 discovery, Arecibo, Dave Galt and Peter Nosworthy. But I raise the question, where are all the satellites? We've got history with this because we had those early claimed discoveries made with visual observations, which unfortunately were never able to be confirmed by other techniques for whatever reason. And visual observations are always have real problems of being able to relook at the, well, you've got nothing to relook. All you've got is an assertion of, oh, I saw the star blink out, and you rely entirely upon what the observer reports, and you can't verify it. Well, statistically, when you look at Johnston's archive, you find that of the first 5,000 asteroids, 118 are known to have 1 or more satellites. That works out as 2.3% of those asteroids have satellites. In 2020, we observed 876 occultations by 586 asteroids. Statistically, 2.3% of those were an asteroid that had a satellite. That's an asteroid that has a known satellite, if you like. Well, no, you'd expect 2.3% to have at least to have a satellite. So last year, we should have had 13 asteroids or 20 events should have involved an asteroid with a satellite. And we observed, well, two known, a discovery and a known satellite and a suspected one. So 0.2%, 0.3%, and we should have had 2%. We should have had 10 times as many as we observed. So why so few satellite detections? And that raises questions of tied up with the history of satellites, tied up with what we did with visual observers, which has probably coloured a lot of our thinking in the last decade or so, plus also issues of establishing proof, if you like. So this is an occultation event of 2018, November 9. It was an event observed in Europe, and I have deliberately removed any plot of the asteroid on there. So you can treat this as being scale independent. And you can see this observer, a video record, 2 events. What are the 3 possible, well, there's 3 possible explanations. Is it a double star? Is it a satellite? Or is it graze of a dog bone asteroid like Cleopatra? I mean, the Cleopatra has got 2 lumps separated by a relatively thin section. So you could imagine the lump at both ends with the star managing to clip both lumps and miss the bit in the middle. So how on earth, if we get such a recording, do we decide whether it's got a double star, a satellite, or a graze event? So some basic criteria to go through. Statistically, a double star is the most likely explanation. However, there's an important issue with a double star explanation. When you have a double star, if you have 2 stars of equal brightness in a double star situation, the combined magnitude is 0.75 magnitudes brighter than the individual stars. The consequence of that is that if you have an occultation of a double star, assuming the asteroid is not visible, the magnitude drop of both stars, the magnitude drop of one of the components of the stars will be no more than 0.75 of the magnitude. And the other one could be 0.75 or 10 magnitudes, the faint component. Grazes, we've had a number of events over the years where a graze is a real possibility. And when you look at shape models, you can see that for some of those or many of those events, the shape model has got a flat side where the star is passing. So a graze is quite plausible. In fact, quite likely, definitely an explanation for quite a few of those events. You need to think about the scale of the whole situation. The separation between the 2 events, how does that compare to the expected size of the asteroid? And if it's expected to be an elongate asteroid, such as a dog bone asteroid, if you can find out whether there's light curve variations, which indicate the presence of an elongate asteroid. All things to be brought into consideration. For a satellite, you need to establish equal light drops with both allowing for variations in camera response and various other factors. You need to establish that you've been able to record stars to at least 1 magnitude fainter than the star you're monitoring. And you also need to have the magnitude drop being rather large than 1 magnitude as well. Otherwise, you've got a serious problem trying to distinguish between a double star explanation and a satellite explanation. Now, with the Arecibo event of Peter Nosworth and Dave Galt, we spent a fair bit of time going through that, and Peter explained, trying to find stars. Well, he found stars down at 15th magnitude, and that was critical for the conclusions before the second event of establishing that it was not a double star, and the separations of that, the Gray's consideration was excluded. Now, other explanations, you might think about, hey, is there a bird flying over or something like that? With the Arecibo event, when we did the calculations like that, we figured out that what was flying over to explain the thing was something which was, well, if it was in the atmosphere above the telescope, it wouldn't be a bird. It would be something about the size of a football field. Which was sort of, actually, I think it might have been even larger than that. So you'd have to have a bloody large bird to fly in front of the telescope to see this event. A lot of the explanations about birds flying in front of the telescope, that type of explanation, when you start doing the mathematics, those explanations are untenable. Now, this couple of slides here is something for people to think about in terms of measuring your videos. The question is, how good is our event accuracy? This first slide, and Dave Dunham showed this event. The event's superimposed over an image of Ganymede. Ganymede is, for all practical purposes, circular with no significant mountains. You can see here the various reported events with the reported uncertainties. And I've highlighted a few events there where the edge of Ganymede is outside the uncertainties of the chords, of the observations. And the next slide, Umbriel. Again, this was observed in America. And again, I've highlighted or indicated a number of situations where you have to, the best explanation is there is a fundamental problem with either time base or analysis of the recording. There's no other reasonable explanation for the type of differences. Look at the heavy arrow at the left above the E. Here you have on that chord at the right-hand end, you have there's two chords there, the right-hand end, both observations align. At the left-hand end, there's a significant time difference between the two. And the particular event I've highlighted, small uncertainty, huge difference from the actual expected event time from that fit. I fear that we have some issues with our observing, our measurement people in terms of getting reliable times out of the video recordings. The one where I've got it highlighted with the big arrow on the left, something clearly wrong with the reappearance event. Sometimes I see situations where one chord, the whole chord is displaced relative to the other chord, and that's usually a time-based error. And they most commonly occur if somebody's using NTP as their time-based source. I guess what I'm saying here is I can't emphasize enough that out of all this stuff, extracting accurate times is highly important, and accuracy is not the same as, I'm probably expressing this badly, accuracy is not the same as reported precision. I mean, if you look at that one again above the E, the claimed uncertainty was very small, but the accuracy of the event was very poor. The accuracy of the reported event did not match the reported uncertainties. And that's an issue of general concern. Okay, now I'm going to flip through here a number of events, just a random selection from around the world, just to illustrate some of the nicer events we're getting. They're all multi-chord events. Where possible, I fitted them to shape models, so you can see the differences between the observations and the shape models. A couple of these, hopefully I'll point out, but keep an eye out for the inconsistencies in adjacent chords. That's a nice fit there. The asteroid, our measurement is consistent with the satellite measurements, but our uncertainty is much less than those. Here's an event without any shape model. The chords, the times are all consistent. If you look at the two blue lines close together, chords 1 and 3, 1 has got a small uncertainty, 3's got a large uncertainty. They're within each other's uncertainties. The same for the next two chords down. It's that type of situation where sometimes I do manual weighting of the observation, so then that one, chord 3, I might weight as a lower weight than chord 1. This is a rather nice event. It's fitting an ellipse to this asteroid is meaningless, and there's no shape model. It's an interesting shaped asteroid from this profile. It's a pity that the second topmost chord had large uncertainties, but that's fact of life. Here's a case where a fitted ellipse and the shape of the asteroid are rather different. And here there is a significant difference between the center of the ellipse and the center of mass of the asteroid. The center of mass of the asteroid is marked with that funny symbol in the middle. The center of the ellipse is a significant different distance to the right. If you look at the chords, the first set of chords to the left of the center, there's two very close chords. If you look closely, you can see that the two reported times, their uncertainty bars do not overlap. There's a bit of an issue there. The other issue you can note is that one chord is displaced relative to the other, which suggests that as between those two chords, there's a time-based issue, whether it's camera delay correction or some other issue. There is something that's an indication of an issue with one or other of those observers' recording systems, analysis systems. This is an interesting odd-shaped asteroid observed in Europe. Not sure why I particularly included that. There's nothing particularly exceptional about that one. Paris. you have to wonder when you see events like this, when you look at the chords to the left, are those, particularly at the bottom left, the scattering of those, is that indicative of a real shape of the asteroid or measurement errors? I would like to think I had full confidence in the reported times for those events. I have my reservations. And when you look at the green and yellow chords to the right, the yellow chord compared to the green chord is plausible, but you're looking at it, is there a time-based shift involved in it? Should it be up to the top left a bit more? Who knows? That one also happened to be a double star event, and the separation is indicated with the blue lines in the center, 7.6 milliarc seconds. Now this one, also a double star event, 76 milliarc seconds. Look at the chord distribution at the bottom. I challenge anyone to come up with an argument that says all of the bottom 4 chords can be explained on the right-hand side by the shape of the asteroid. There is, don't know which ones are wrong. It's interesting, those 4 observers all agree on the reappearance side. But on the disappearance side, there is significant discrepancies which are inconsistent with any plausible shape of the asteroid. Excuse me, Margaret. Just my son on the phone. Now, next one. Padua. It's possibly, well, it's a nice result there, but have a look at the bunch of chords in the middle on both the left and right-hand side, particularly on the right-hand side. Ask yourself whether the scattering of those points is plausible, having regard to plausibly explained by the irregularities in the edge of the asteroid. An interesting question, and I'll put it no more than that. And here's an event of Pallas observed in Europe. Ties down its shape model to one of the several, but the shape model is clearly not quite right. And this is Hermione. A nice fit to a very elongate, or well, I think it's flattened. I think we're looking at side on, I forget now. Asteroid, again, assuming you can rely upon everybody's times, the shape model isn't quite right, but that's a very recent shape model, and every reason to believe it's a reasonably good model. And our diameter estimate from that is significantly larger than 2 of the main asteroid satellite determinations. And that's it for that one. Any questions on that? Are there any questions?
I have a comment.
Yep.
On the double asteroid deficit issue. You know, if most of these are one chord events, you would have to have the satellite a long path, whereas a satellite could be anywhere.
Exactly.
So, you know, a 10% detection, I don't think is out of line, frankly.
Yes, two things about that. We've had a number of our detections have been from people who've had miscords. But the other issue is when we look at the older observations, we've had a number of reports of occultation events by people who missed the main asteroid, and we've interpreted them as being very suspect. And part of that is, and part of what I'm suggesting here is we probably need to have a significant reconsideration about how we consider our observations in the context of satellite detections. Our history with what happened in the before 2000 has led us to a position of being very skeptical of secondary occultations being explained by a satellite. And I guess I'm suggesting that we should be taking such events much more seriously and go through a fairly rigorous process of investigating them. And that means having a video record. Visual observations, quite frankly, are unreliable. There's too many possibilities. You might be a blink or whatever. We need to have video records, and those need to be analysed to the death, so to speak, and preferably using more than one measurement tool, so that you've got various means of independent verification of what the recording shows. And you've got to do an analysis of is the light drop sufficiently great to say that it can only be a satellite. You've got issues of how you determine the limiting magnitude of a video recording, and you cannot do that from a straight measurement of a light curve on the video recording. You're not, the bottom of the video recording is not magnitude 20. It's some brighter magnitude, and you've got to go through a process of actually establishing what the limiting magnitude is. And that means you've got to have stars which are rather more than one magnitude fainter than your target star, preferably at least 1.5 magnitudes fainter, so you can positively exclude the double star event. So, I mean, I think we should be doing much more to consider some of our observations as being possible detections. We've got one in Europe, we're under investigation. I've seen a recent one where I think satellite detection is likely to be, is a real possible explanation for the light curve that's obtained. Yeah.
Question about the umbral plot that you showed.
Yep.
The chord that you were talking about mostly as being a likely timing issue. So there were two dots or bars outside the circle. But there was one just inside. So is that large error bars on the occultation, or from the way you were talking, I got the impression that the two outside were the error bars on that observation. So.
I'm trying to bring that. Why won't this show? Is that showing on? Is that I've brought?
No, it's not
No.
showing.
Oh, there it
Yeah,
is.
Now
there
we're
it popped in
saw
for
it for a moment.
Oh,
There it is.
okay. I'll see if I can. Oh, now I've really stuffed it. It's disappeared. Can you see anything there?
I did
No.
briefly.
Yeah, I'll stop. I need to stop sharing my screen. Oh,
The
hang
event
on.
with the large, thick arrow.
Yeah, let me. It was an issue of PowerPoint. Let me share again. Share screen. And here, yep.
There we go. The large, thick arrow there.
Yep.
There, it's pointing down at two dots or bars, but then there appears to be a third one just inside the circle.
Yeah, that's
Yes.
two chords on top of each other and they don't agree.
Ah, oh,
Yep.
okay, okay.
Yep.
So,
So one,
two observers on very nearly the same chord.
yes, and when you look at the right-hand side of those two chords, two observers are in agreement on the disappearance.
Mm-hmm. Yes,
And,
it just appears as one very large square dot on my screen. So
I hope one of those wasn't mine. Can you tell us who those people are?
For everyone that's in attendance, which is looking at this, I will in jest say that's your observation.
It would be nice to have feedback.
for you. Yeah,
If there is a problem.
Gary in Florida, I've got two questions for you. You were talking about successful events and unsuccessful events. I wonder if you could outline the characteristics of each. And I wonder if there's some way to give observers feedback so they can improve their success rate.
Okay, some of those events are wind affected, or cloud affected, so the observer only gets one of the two events. Some of them, a small number, a relatively large asteroid, and the observer records an event of, say, 0.1 of a second, disappearance or reappearance, 0.1 of a second. And when you're at that level, you've got to wonder about whether it's a noise event or it's a real event. And when you start doing the mathematics of the probability of getting such a short event on a large asteroid, it's stuff all. Sometimes you get two chords, a two-chord event, where there's a huge discrepancy in the location of the chords, such that you know that at least one of the chords has got a serious time-based problem, and you don't know which one it is. So to report anything from it, which one do you believe? So you finish up saying, well, yes, you both got the observation, but because of the discrepancy, you don't know who to believe. And when you see those, and it doesn't happen very often, but that also raises concerns about single chord events, particularly when observers go after a small magnitude drop event. If you've got a single chord event with a magnitude drop of 0.1 of a magnitude, then I will frequently say, I want to see the light curve. because over the years I've seen enough light curves in that type of situation where your basic reaction has to be, you've got to be kidding. There's a psychological issue involved in all of this. When you put all the effort into trying to observe an occultation, there's a natural desire to interpret your recording, if it's noisy, in a manner where you have an occultation event. If your the desired outcome was to have a miss event, and that was in your mind, oh, I've got to have a miss event, no matter what, I really want to have a miss event, those light curves might well be interpreted by the observer as a miss event. Now, the work that Bob Anderson has been doing with IOTA, thanks, Bob, for the clarification of the pronunciation, that does a lot to address that issue. But with some of this stuff, we've got to take a fairly hard line. In reporting astrometry to the Minor Planet Center, which goes through to horizons, because we're dealing with very high precision, which has a significant impact on the orbit solutions, we can't afford to be in a position where we report an astrometric position on the basis of, I think the asteroid was there. I think I had an occultation event. The only position we can take when reporting our high precision astrometry is one of, I know an occultation occurred. I know the asteroid was there. So when there is any reasonable doubt about the existence of an occultation event, or the consistency of the chords of an occultation event, yes, it's maintained in our database, but we do not use it for any astrometry. And when you have those conditions, you can't derive anything about the size or shape of the asteroid as well.
So I guess the bottom line is, if it's an iffy observation, it can't be used, and that would be defined as an unsuccessful event.
Yes, I'm using that term unsuccessful. Let me just, in the database that we maintain, let me just open up my program to make sure I've got the right wording.
I noticed someone in the comment field made the comment that if it's less than one, they don't attempt the event. And that makes sense, where you're going to put your time and effort. If you're going to get something that's no better than iffy, then maybe better to not report it at all.
Except if you've got other people who have success, then the correlation between the chords can confirm it.
Yeah,
I think a magnitude drop of 1 is too coarse. I think most people would be able to handle down to about certainly 0.5 without too much trouble. With the small magnitude drops, the issue is you've got the star rather brighter than, sorry, the asteroid rather brighter than the star. And the absolute essential thing you've got to do is make sure that the star is clearly visible by itself. And then you have to try to ensure that the star is not saturating, and that you can deal with by defocusing. Or if you use Risto's Tangra, measure the video using a point spread function method of measurement rather than aperture measurement. It's a totally different way of measuring, and a point spread function measurement can handle saturated images.
Yep, very helpful. Thank you.
Okay, should I go on to my next?
I think so, David. I would just go on to the next presentation, and thank you for this. It's been very interesting.
Now I've got to figure out how to close this presentation. You know, bear with me for a second. Just got to get this presentation closed. Now I can open up the next one.